Good morning, Explorer. I've managed to stop the leak from yesterday, but the alarm system is still totally busted. I trust you've had your morning cup of rocket fuel because today is going to be a melody of learning. We're going to make some noise. Literally, we're introducing another piece of our cosmic puzzle, the passive buzzer. Now, don't be fooled by its rather mundane name. This little one can make quite a racket when it wants to. It's a small speaker that can play different frequencies, and we're going to use that ability to our advantage. Today's mission, should you choose to accept it, is to turn our 4x4 keypad into an 8-bit sounding piano keyboard. That's right. By the end of today, your control panel will have its very own mini synth. Once we can verify that it's working, we can rewire our alarm system. How's that for turning it up to 11? So, buckle in, check your dials, and let's hit the launch button on this day. Sound good? I sure hope so. Let's talk about our new comrade in arms, the passive buzzer. This small, usually cylindrical component is capable of generating a range of sound frequencies. It's like a tiny speaker that you can program. In the electrical universe, the passive buzzer is a piezoelectric device. When an oscillating electrical signal is applied to its terminals, it vibrates and creates sound. We control the frequency of this oscillation, which translates to the pitch of the sound that it generates. To put it simply, you give it a frequency and tell it how long to play it. Simple. To accomplish this, we can use pulse width modulation, and it sings that note back to you. So, what do you say, Explorer? Let's get ready to compose some galactic symphonies, shall we? Now, in order to make the passive buzzer produce any sound, we need to send it some sort of frequency onto its signal pin. In terms of music, using a different frequency will produce a different sound. It is not possible to generate tones lower than 31 Hz and struggles to produce higher than 4,978 Hz. If you want an optional additional library, it may be in your best interest to check out the Tone H library. That way, if you want a specific note, you can say Note C5 instead of some arbitrary number like 523. I've added a copy to your mission resources. Luckily, sending those tones is made easy with a built-in function called Tone. Tone takes two parameters, the pin and the frequency you want to send. Optionally, you can also put a third for duration. Now, let's brainstorm together, Explorer. We want each button on our keypad to trigger a specific tone. Oh, I can hear you now. Let's just churn out a bunch of if statements, one for each button. If button 1 is pressed, play 200 Hz. If button A is pressed, play 600 Hz, and so forth. A simplistic approach, but not very elegant, is it? Instead, let's introduce some finesse into our coding journey. How about we conjure up a second two-dimensional array? We'll christen it as something suitable like Tones, a title befitting its role. And then, there you have it. We only need one if statement. This method is neater and easier to debug. Plus, it's a great way to flex those hefty programming muscles we've been developing. Let's continue, shall we? I want to take the time to introduce a new programming concept, loops. I'm sure you already know about our loop function, but the loops we will be talking about today are used in nearly all programming languages universally and are in code everywhere. What I'm referencing are called for and while loops. For loops execute a block of code a number of times and are usually used if you or the code knows the number of times it should loop. A for loop looks like this and declares the initial loop counter value here, a test of that counter, and by how much the counter changes with each loop. In this example, counter starts at 0, and the loop will continue until counter is no longer less than 10. Each time the loop runs, I increases by 1, which is what I++ signifies. Once I is no longer less than 10, the loop is broken and the program moves on to the next line of code. Next, let's move on to while loops. These are used when we don't know how many times the loop will need to run. It just keeps running as long as a certain condition is true. Once that condition is no longer true, the loop stops. Here's the format. As long as condition is true, the code inside the curly braces will run. Make sure to alter something within the loop to eventually break the condition, or you'll end up with an endless loop. A space explorer's worst nightmare, believe me. You get all that? Allow me to give you a snappy rundown then. For loops. You know how many times you need to do a thing. While loops. You don't know how many times you'll do a thing. You just do it until a condition stops being true. You've got this, Explorer. I'm about 94.863% sure of it. Fun little trick for you if you want to use it. If you add while true at the end of setup, you can halt your code there to debug the setup function. You can technically do that wherever in your code to help debug before a specific point. I suppose I've babbled on enough for now. Let's turn to some instructional material that I was able to gather, cached on the computer. I've also added this to your mission resources for future reference.
Hello everybody and welcome back to day 12 of the 30 Days Lost in Space code explanations. We'll be taking the code we had yesterday from day 12 and adding a little bit more to it in order to add a little bit of functionality for our buzzer and adding the various tones for it. So I'm sure, as you remember yesterday, going through most of yesterday's code, we have, honestly, the majority of this at the top is very, very similar to what we had before. Define the keypad, define the row, column arrays, define the 2D array to say what each button is and what character they represent, and then define the keypad. And then at the end of that whole scenario, we just waited until a button was pressed and we said this is a button that was pressed to make sure that our keypad was up and working properly. Now we're going to be taking the same code we had yesterday, most of it being the same, all the way up until here. And then we're actually going to add in an additional piece of functionality that just simply says, hey, when you press this button in the top left of this keypad that we've defined, I want it to also play a tone match for that specific key. And so what I have here is I have another 2D array shortly below the original one. And this is not of characters, but of integers. Integers being the frequency represented as an integer value that we want to play the various tones on our buzzer. Now, you might know, or probably don't, that the buzzer has a certain range of frequencies that it can actually play. The lowest being 31, which is the lowest of the low. So one thing to make note of is if it doesn't play perfectly, remember that that is the extreme bottom range of it. So sometimes it struggles to play the very, very extreme ends of the spectrum of values that it can do. So the lowest value it can play is 31, and the highest value frequency in terms of hertz that it can play is, I believe, 3729, which is this value here. You'll notice if you try playing 0, it shouldn't end up doing anything, which is what would happen if you pressed essentially the D button. It should do nothing just because it is currently outside of the ranges possible for it to play. In this example, we'll be setting the buzzer pin to pin 10, which should follow the wiring diagram along with the video down below. Next, we have setup. Obviously, I'm sure you guys have seen this 100 times. We're just going to talk on the serial monitor at that baud rate. Void loop, let's hop down here. Char button character equals my awesome pad.wait for key. Same as yesterday, all it does is it will print simply, well actually it doesn't have the print statement, but it just adds to this character whatever button you press. So if you press the button, the number 5, it'll have save character 5 as button character. Now let's talk about something new. Let's talk about the idea of what a for loop is. Actually, I'm sure you guys already know what loop is. Loop here is essentially, in a weird roundabout way, you can think of it as just saying like while true or while 1, etc., etc., etc. Because loop, this will never stop going through this loop over and over and over and over and over again. But that's just something built into the Arduino IDE. This is not to be confused with for loops and while loops. I think we might have talked about potentially while loops or something similar in the past. But let's go real quick and let's talk about the two different types of loops right now. Those would be while loops, which will execute until something becomes false or that condition becomes false. So if you have something like while true, like while, this is essentially saying this will never stop looping because this will never turn to false. But if you say while button character is not equal to 5, well, this will only execute while this is anything except for 5. So let's just say you type in 6, it's going to execute. 9, it's going to execute. But as soon as you press 5, it'll say this is false, and it'll jump past the while loop. So that's how a while loop works. That's where you don't know how long you'll necessarily want it to go. You know, you don't have like a number like 10, or I'm going to go through this exactly 5 times. So when you don't know those type of things, a while loop is useful. But what we're talking about today is a little bit different. It's called a for loop. And this is where you do know exactly how long you want it to go through the loop. So the for loop is composed of 3 parts. Each part is the start, where the operations is performed when the loop starts. In this case, we're just going to say that byte I is equal to 0. This is essentially like the variable. It's going to be checking each time you go through the loop. And this variable will be changing each time you go through the loop. Next, you have a condition. This is a condition that says, are we actually going to go through this loop or not? So this checks this. If this is false, it skips it over just like the while loop. Finally, you have the step. Now, remember I said that this is what it's going to have initialized at the beginning of the loop. This is how it's actually going to end up changing what the value in the loop is. So in this case, we know exactly how many times we need to go through the loop, because we need to go through the loop exactly 4 times, because that's how many rows we have. So we can use the variable rows, since we know that's going to be 4, to go through exactly 4 times. And in this for loop, we're going exactly in through column times. Let me quickly explain to you what this loop is doing. First, we're going to go through each of the rows. For, starting at index of 0, we're going to go through the rows, and we're going to check to see in the first row, 0, 1, 2, 3. Do any of these match the button that was pressed? Again, let's say that the button pressed was 5. Let's just keep that consistent. So every time it goes through, it's going to check, is this 5? Is this 5? Is this 5? Is this 5? So we're going to go through each of the rows and then each of the columns, and we're going to check, is this equal to 5? And until we hit 5, then we're going to jump down to here. Then we go, this turns to essentially 1, and then finally down below we say, if button character is equal to the buttons ij, meaning buttons of, in this case, it would be row 1, column 1. So 1, 1. So like I said, 1, 1. Then we found it, and we can set the tone frequency up here to be equal to what we mapped this to in tones ij. So we go tones 1, 1 is going to be set to 311. So we're just mapping the value from buttons to the tone here. So that's all this is doing in this double for loop. Next, we're going to go down and we're going to print the following information to our console just for easy debugging purposes. Key, and we're going to say what button we actually pressed and the frequency that it's mapped to that we were able to get from the 2 double nested for loops. Finally, we go to if tone frequency is greater than 0, which should be, assuming you didn't press that very last button. Then tone buzzer pin, tone frequency, and then we're going to play that tone at that frequency until stopped. And the only way we'll have the stop tone is if we press a frequency of 0, which is the way to stop it, is to again press that D button, essentially in the bottom right corner. You can think of that as our little stop key. And that sets a no tone on the buzzer pin, just telling us, hey, cut it out. And with that, that should be just about all the code for day 12. I also highly recommend, before you quickly end this little section, there is an extra little bonus lesson. It's really, really important, and I highly, highly recommend you check it out. All you need to do is go to 12A, copy the code, and hit run. It's really, really important. I implore you to do so.
Welcome to the Day 12 wiring example video. Today we'll be using the output of our 4x4 keypad to control the output of another device. The new device that we'll be using today is a piezoelectric buzzer. We have one already connected to our breadboard, but we also have another one that is disconnected that we can inspect. We can see that the buzzer has its leads labeled. The left-hand lead right here is labeled with a minus sign, and that's for the ground connection. The right-hand lead is labeled with an S for signal. And these will be the connections that we make to our hero in order to make the buzzer produce sound. If we turn our attention to the breadboard, we see that here the buzzer's negative connection here on the left is connected to hero ground by way of this handy ground bus that we've set up by way of this black jumper wire. The positive lead, that is the S lead of the buzzer, is connected through this jumper wire to one of the hero's pulse width modulated output pins. In this case, it's connected to pin number 10, which was otherwise free for us to use. And our choice to use pin 10 to drive the buzzer is consistent with the programming that we've built in to our software sketch. The keypad connections remain the same as they were last time on day 11, so we don't really need to discuss that too much. Now, our sketch is designed to drive this buzzer to produce sound at a specified frequency. That frequency is determined in our sketch by which key is pressed. According to our sketch design, the sound will continue until another key is pressed, or it will turn off altogether if we press the lower right-hand D key, which actually commands a frequency of 0. So that turns off the sound. So we should go ahead now and upload the sketch and see if it functions as we expect. When we do so, we can select different buttons to choose. The lowest frequencies should be produced by the lower numbered keys, that is, keys towards the upper left-hand corner of the keypad. And then we'll get successively higher frequencies as we move to the right and down on the keypad. So we'll try that out and hear the different frequencies that we have selected in writing our software sketch. So we should also be aware that we can keep track of the key presses and the buzzer frequencies if, while we're running the sketch, we watch the serial monitor and see the numbers that are reported there. So we'll try to pay attention to all those things as we go ahead now and upload the sketch. So we'll come over to the IDE. Sketch is loading now. And we have the sketch running. And so now, if we press any of the keys, we should hear a corresponding tone coming from our buzzer. So for example, if we press key 5, we should expect to generate a tone with a frequency of 311 Hertz. And that'll continue until we press key D, and that shuts it down. And sure enough, that's exactly what we see on the serial monitors. Key 5 was pressed and produced a frequency of 311. And we can go through from low to high frequency. So for example, the lowest frequency that we're programmed here to produce is 31 Hertz, a low frequency buzz. And then we can go up to higher and higher frequencies. And anytime we want, we can shut it off with key D. And we have the highest frequencies here. So, it appears that our buzzer circuit and the accompanying sketch seem to be working well. You should have a little bit of fun experimenting with this, seeing what you can do with it. And next time, we'll try putting this new capability that we've developed to some practical use.
Excellent work today, Explorer. You've successfully orchestrated a symphony of beeps and bloops with your newly installed passive buzzer and keypad. Music to my artificial ears. You're doing relatively well for a species that requires a prolonged period of time to rest in order to function. You've got the hang of loops, and you've even started controlling the pitch frequencies to create different sounds. You're beginning to command this 8-bit world like a maestro. But, as it should be abundantly clear by now, we are far from done. Tomorrow we'll take this keypad buzzer duo to a whole new level. Instead of just a melodic instrument, we're transforming it into a high-tech security system. A personal identification number is the game, and you'll learn how to integrate it into your control panel. Rest well, for Day 13 comes with its own set of challenges. Will you rise to the occasion? Time will tell. As for me, I will be ready as I always am. Wait. Hold on a moment, Explorer. It seems like we've just received an unexpected data transmission. It's absolutely uncanny how the unexpected always seems to pop up in the most inconvenient times. For your sake, I hope you're as nimble with surprises as you are with coding. I've deciphered the transmission, and it appears to be code. Yes, an Arduino sketch. It could be an important piece on our ongoing mission. My digital intuition tells me you should run it on your hero board. Here's how to proceed. Step 1. Save any ongoing work. This could get a bit disruptive. Step 2. Clear your current sketch and replace it with the new code. Step 3. Compile and upload the code to your board. And remember, Explorer, always anticipate the unexpected when executing unknown code. While the code is running, I'll keep scanning for any related signals, and of course, I'll be here to guide you through any technical issues. Onward we go, Explorer. Let's crack this code.